Hello, everyone, and welcome back to another Q&A session of the Vampire Workshop. So today we're going to focus on Skyrmions and unit cell files, and we have as well Andrew, who will going to be our co-host on the statistics tutorial. So if you have any questions related to these tutorials, well, if no one doesn't have any question yet, I'm going just to start with an additional thing to the tutorials I've done on Skyrmions. So for the visualization part, I've been using just a simple script in GNU-plot. However, there's also the method to plot this via Povray, in which you can obtain much higher quality pictures. So if you've been through the visualization tutorial, there's a simple way in which you can plot that. So that's an additional thing to do for this kind of tutorial.
Yeah, so these sort of Q&A sessions should be making their way onto YouTube at some point. I think yesterday should be up already, I think. But yesterday's visualization session that me and Dan and Mara and Richard were in, Dan explained sort of, more about how the VDC tutorial, how the VDC tool works and how to get the most out of it, because Povray is, by nature of being a ray tracer, is quite expensive to run on lots and lots and lots of data. So getting the best performance out of that, so you're not waiting hours for renders. And Skyrmions obviously are a really good example of something that's really nice to visualize spin by spin, because well, they're quite small to begin with, so you don't have you don't lose individual spins in just a large blotch of color, but also they're defined by their very small scale localized changes in spin direction. So it's important to be able to visualize those effectively on small and on large scales. Okay, Richard says that the video isn't up yet because the internet's being quite slow. I imagine YouTube's having some difficulties at the moment, given how many people are at home using it.
So on the Skyrmion side, I don't know if you have been watching the previous Zoom meetings from yesterday. There was a question regarding whether to use the inbuilt DMI interaction if you have kind of multiple layers, and how to do that if you have multiple materials. So in the tutorial, I've presented both ways, if either to use a unit cell file or the inbuilt function. using the unit cell file, you have a bit more control of the system you're generating and your actual Jaloshinsky-Moria interaction. With the inbuilt DMI function, you need to be a bit more careful in the sense that you need to choose carefully your cutoff radius that will calculate this interaction and so on. But this feature is very very important when you have alloys where you have a random placement of atoms. So it can be very powerful and useful for different kind of materials.
Okay, it's a good time to a question.
Yeah, go ahead.
Okay, because my work is about ultra-fast spin dynamics triggered by femtosecond laser pulse. So I mainly use the two temperature model in one pair. And recently I got some results in Skyrmion materials using laser pulse in my experiments. So I want to try use one pair to give some simulation. What I know from the video, if we want to generate skirmings, we have to use a field cooling model in the one pair. And but if I want to see the response of skirmings to laser pulse, we have to use another model, the two temperature model in one pair, I think. So I have to write two input fields, but these two input fields they are separate, I think. So my question is, how can I put the skirming state generated in field cooling model into the two temperature model? There, the skirming state could be the initial state. And so I'm wondering, it's possible to write a single input field to combine the field cooling model and the laser pulse model.
So the easiest thing to do for your problem is to use checkpoints. So basically you run your field cooling or zero field cooling simulation and you save the final configuration in a checkpoint. And then you can restart your laser pulse simulation, the two temperature model simulation, starting from that final state that you obtained via field cooling. So you don't need two inputs. You need one simulation in which you obtain once your Skyrmion state, so your final state, and then you take that state always and use it in the two temperature model.
And this obviously means that you can run lots of different laser simulations on the same input, essentially the same Skyrmion lattice or weave or whatever, over and over and over again without having to rerun your field cool to regenerate your Skyrmions, because you have that final state, you have that final spin configuration already. So it kind of seems a little backwards if you were just, especially if you think of it from a sort of experimental point of view, because in an experiment you would always have to generate new Skyrmions, then run your laser simulation, then new Skyrmions. Then obviously we can skip generating new Skyrmions over and over and over again, and run on this same Skyrmion lattice, and then you only need to re-field cool if you need a new Skyrmion lattice. So it allows you to play around with the laser simulation a lot more. But generally, most of the programs in Vampire are designed in such a way that if you want them to interact with each other, it's more efficient to save the output spins and then run the new simulation. It's a bit because of things like loop unrolling, it becomes a bit messier if you wanted to try and get it to do it in one go, and actually you'd end up wasting more time down the line. So the easiest way is to use these checkpoints. There's 3 checkpoint flags. There's save checkpoints, or it might be checkpoint save. There's save, load, and continue. Think of the 3. Save and load are save checkpoint and load from checkpoint. The load one will fail if there isn't already a file for it to load from. And then continue is like load, but it won't fail if there isn't one. So it'll only continue if there is one, and if there isn't, it'll start from scratch. I think that's on develop. It might not be. But yeah, the save and load are the two ones that are important, and they are in the manual.
And restart, in which basically you just take the checkpoint you have and restart your new simulation with those parameters saved there. So for your case, I think you will need the restart.
Okay. Okay.
So just one additional thing. So we actually have a collaboration on this, Skyrmions with the ultra-fast bit. So in a couple of months, there will be a manuscript on the protocol and how to generate this with the Vampire, if you're interested.
Okay. Okay, thank you. Another question. Another question is about a UCF file, in which how to add the DMI. From the video I see, if there is a simple cubic and only one atom in the structure, so this structure is very high symmetry. Adding DMI in this case is not very difficult to understand, but when the structure is more complex with the symmetry broken, that means in a unit cell there are several atoms without any equivalent. So in this case, it's still too big challenge for me to figure out how to create UCF file. Although I know how many atoms there, and I know their coordinates. Even I know how many interactions there, but I don't know how to add the DMI in the right place in the UCF file.
So for that, you need just probably some external code to read your coordinates, and based on the coordinates, you can generate the neighbor list. And based on that, you can get the DMI vectors, so the directions as Z cross product. So if you just want like interfacial DMI, then you have the out of plane cross product with the relative distance, and you add that into the exchange tensor. So basically the principle is the same, but you will need some sort of external tool in which you want to construct like much larger scale of interaction.
Sorry, what do you mean the external source?
Sorry?
What do you mean the external source to know its structure?
So for example, if you have a complicated structure, but you have the positions.
Yes, I know.
You know the crystal structure. You can always calculate like, you can make like a simple code like in Python or wherever, where you loop through your atoms and calculate the neighbor list, the distances, and based on that, you can calculate the DMI vectors. And add that afterwards in your unit cell file and in the tensorial exchange. Okay. So for simple cubic lattice or I don't know, maybe as well hexagonal lattice, it's easier to do, by hand. But whenever you have a more complicated system, they need something externally to generate that. Or you can try to use the inbuilt DMI method, which kind of does that, but behind the scenes inside the code.
So if you want to talk about the actual Python or anything like that, we can have a chat about it in Slack in a minute. But I mostly work with the 214.1 phase of ferromagnets, which is a 64 atom unit cell. And so I have a Python script for reading in a sort of a crystal structure and then generating neighbor lists. So if you want to have a look at something like that, we can have a chat about it in Slack.
Okay, how can I see that?
Well, I'll do it at the end of the thing. If you can hang around at 11 when we're done the actual this, I'll have a chat with you on Slack if you want.
Okay.
I think you've been invited to the Slack, Richard. I think people have all been invited, if they're not.
Yeah,
They should.
there is like a channel especially for Skyrmions.
I just wanted to point out one thing for the checkpoints. That if you do a simulation in parallel, then you will have to use the same number of cores when you restart your simulation. Otherwise, the checkpoint won't be able to work because you also store the coordinates. So if you save the coordinate over 40 cores and then you try to run it over 20, then you will have some problem and the simulation will fail. So just mind that. So if you do a simulation in serial and you save the checkpoint, you will have to keep it in serial. If you do it in parallel, just do it with the same number of cores.
So generally, the number of cores is reliant on number of atoms anyway. So you would rarely find a situation where you'd want to be changing. If you're looking at the same system, you wouldn't often want to be changing the number of cores anyway, because the amount of time a simulation takes tends to increase just with number of atoms, really. So
well, the other one would be the Monte Carlo case, but
number of atoms is the sort of the primary thing that you do decomposition with. There isn't much. You aren't going to get a much. If you're running hysteresis, say, it's not going to want a different number of cores to if you're running a Curie temperature simulation. It's still going to want the same amount of cores for the system. So you're unlikely to find a reason why this is going to be a big issue.
yeah, I mean, I would just point out though, in case you find the
Definitely.
the error and you wonder why, and I change the number of cores. Maybe, I mean, the easiest case would be you change your cluster or a queue and something. But anyway, it would just to point out.
Okay, thank you. You answered my questions. Thank you.
So there's actually a question from Richard. How easy is to visualize the chirality of the Skyrmions? Well, I think it depends a lot on the Skyrmion size and as well the temperature. So when you have a very high temperature, the thermal noise might be a bit tricky to visualize the chirality, but in principle you can. But this should be anyway given by, in principle, the sign of the Jawoshinsky-Moria interaction. So I think it's kind of easy to know what's the chirality of your system.
May I ask, hi, this is Marek, Chef. May I ask a question? Do you hear me?
Yeah, we hear you. Go ahead.
Yeah, this is also the question for Mara regarding the question of Richard. So regarding the chirality, you just mentioned the sign of a DMI, and I know that very often it is like a story of a source of a confusion on choosing the convention of the sign of a DMI. So I see that in a slide, I looked briefly, you define it, your interfacial DMI is defined as a Z vector product of a UIJ. And we see that in the many papers, there is also alternative convention where they define it like UIJ times Z. So just to stick, and also the second question, I mean, very related to this convention question, which may lead to the confusion, is the sign again, is whether we are talking on a ferromagnet on the top of a non-magnet, or non-magnet on the top of a ferromagnet. So I think that just my question is whether in a vampire you always stick with the same convention when we talk about the sign of a DMI. So you are always using Z times UIJ, and are we talking always, because in your example I see that there is a platinum on top of a cobalt, but there very often we have to look on a cobalt on the top of a platinum, and you see that this will lead to the sign change, etc. And this is so just about the convention. Are you sticking always with the same convention when you implemented all these things? Yeah, related question is whether for the chirality, did you check that, for example, you are getting a left-handed chirality when a cobalt is on the top of a platinum, for example, for positive DMI in your convention or for the negative DMI? Yeah, thanks.
Okay, so related with the cobalt on platinum. So so we use this Z cross UIJ just for this kind of example of the unit cell file. For the inbuilt, it's the actually the cross product between the displacement. So you have the platinum atom that it's mediating the interaction. So you have something like IK cross product JK. So in principle, there should be a convention of signs for that. But honestly, we haven't looked too much on the chirality, trying to do different tests, like changing the platinum size to see if there is a change in the chirality. But I think from the convention should be there.
Curious, when you tried, for example, for the same cobalt, you tried with the HCP or just hexagonal structure, whether your how does it compare? I'm sure you did it, but I'm curious, how did it compare with your simple cubic run? Did you, in order to get the same skill, increase the DMI value, or just how the yeah? Did you run another example with the cobalt another lattice? Yeah.
Yeah. So actually, at some point there was in the chat a very good paper. I think it's something called like Anatomy of Jaloshinsky-Moria interaction, in which they did the calculations for cobalt platinum interfaces, and it's by oh sorry,
Yeah,
it's by you.
This is actually our paper. Yeah.
Yeah, sorry.
Yeah.
Sorry. I just realized now.
Yeah, but therefore I'm asking you all these questions because we did it a little bit different. But just therefore, from experience, I see that there is a if we don't define the convention very well from the beginning, then in some papers you see that there is a negative which is corresponding to left-handed, then another paper is telling it is a positive which is corresponding. But everything is always down to the convention what you use, and we have to. I was curious, and we are going to, of course, to try following your tutorial. I'm very curious. I installed yesterday actually Vampire also on my computer, and I will try to play with it and to see. Very interesting. And yeah, and regarding also yesterday's question, one of the colleagues was asking about the you answered the question, but about the whether the first nearest neighbor, second nearest neighbor, or like layer resolved DMI. If you see, actually, you can see that the second one is already the DMI is much smaller compared to the interfacial to platinum one, which gives the most of it, and that is actually was the case in that paper, and we see it also in others. But yeah, thanks, Mara. Anyway, for I understood the answer.
Yeah, okay. So actually we kind of just looked as well at your paper for kind of getting an idea of the strengths of the DMI usually used for this kind of systems. But related to the sign, I think we just considered what you had in the paper.
Okay. Thank you. And may I ask one more question, if I may? In your examples, we talk about the Skyrmion lattices, and sometimes we can have also the individual Skyrmion. So I don't know whether you had also, did you try whenever you put an impurity or some defect, and how individual Skyrmion is also nucleated? These examples somewhere?
They're not examples, but there is a student in our group, Junlin Wang, who has done a lot of experiments on this. So he's also able to nucleate single skyrmions if he adds some sort of or pinning field or maybe a defect or something like that. So he has done a lot of work on this, nucleating skyrmions via like a small defect in the system.
Okay. Yeah. Thank you. Yeah. Um, if no other questions, yeah, I'm sorry. There is somebody who's asking a request.
That's Richard, I think. So, if you've got a question, feel free to let us know over the mic. That's okay.
So the question from Richard: are there any limits in system size for simulating skyrmions? Well, the size of the skyrmion is given by this interplay between the field, DMI, anisotropy. So in principle, you can simulate any size corresponding to the magnetic parameters of that system. So of course, for atomistic models, there's a upper limit size due to the computational time, but in principle, a couple of nanometers, 10 nanometers, something like that, we can do skyrmion size. Even more.
Is an anti-skyrmion just a skyrmion but with all the spins inverted, or is there some separate definition for that? I'm not really a skyrmion person, so I'm just curious.
I would assume is just inverting the magnetization.
The core.
Yeah,
Oh,
so that
so-
wouldn't be. I mean, yeah, you
So they're
change
inherently.
chirality, and that should be doable via the. Well, that would depend on the exchange interaction substantially. So if you build your interaction so that you can get that, you should be able to.
Yeah, that sounds, in principle, sounds pretty simple. It would be very similar to generating a regular skyrmion if it is just an inversion of spin direction.
Okay, no problem. Then maybe one thing we can point out, referring to the question from Richard, is that depending on how you build your interaction, so say for example you obtain this from ab initio, of course the larger the number of interactions you have, the higher the computational cost of your simulation is. So even though you might have a very small skyrmion, but you have, say, interaction that extend up to 20 neighbors, for example, simulating a 50 nanometers implying thin film could be already quite challenging. So this also might be a limitation. I mean, it usually is a trade-off between, especially if you have in these kind of complex exchange interactions, to how well and how accurately you can parameterize the system, and then how slow will be your simulations.
So there is another question from Richard. Can you scale the DMI over J parameters to represent larger Skyrmions? Yeah, of course you can, in principle, change the strength of the DMI. So you can obtain smaller Skyrmions or larger Skyrmions based on that. So the interplay between these parameters, the field and anisotropy, will give you, in principle, the size of the Skyrmions and also their stability with temperature. So for the tutorials, actually additional, the model there, it's kind of parametric toy model. So it's not really realistic because I have a DMI quite large. I think it's maybe 100% of the exchange interaction, but that was just to get very small Skyrmions. So there will be very fast simulation for a kind of a tutorial. However, if you want to obtain more realistic systems, then you need to have a look at either experimental paper or ab initio paper in which they calculated the contribution from the DMI, and you can use more realistic values for to simulate this kind of systems.
So going back to the question Wei had earlier about unit cells and generating neighbor lists and things, I do this in Python programmatically. As I say, I tend to deal with sort of not massive unit cells. They're not YIG or anything, but fairly big compared to something that's simple cubic. And the general system for generating your neighbor lists and things to go into unit cell files is at least the way I do it is you read in your crystal structure, and then for every atom in your crystal, you measure its distance to every other atom in the crystal. But you also have to include, because your unit cell repeats, you have to include the unit cells around your unit cell. And then you just hold on to any pair of those that is underneath your cutoff radius. And that builds your interaction list. The interaction list doesn't have to be symmetric, or it doesn't have to be nice and simply laid out like a unit file. It just has to be a list of these interactions. It is symmetric in that the interaction between I and J is opposite to the interaction between J and I. Opposite? No, same strength. But yeah, it can purely be a function of distance. And that's how you include all of the correct neighbors. I don't know if, Mara, do you use the normalized exchanges, or do you use absolute exchanges in your unit cell files?
Both. I think the tutorial is done for unnormalized.
Okay, so there's the option for normalized exchanges where you control the strength of your exchange by a parameter in the material file. I do that because a lot of what I do is parameterizing these exchanges, and it's a lot easier to change one number than 10,000, say. So all of mine are purely functions of distance, but if you want to do it with them being absolute, that's fine as well. But yeah, I would recommend something like Python, because you don't want to write out 10,000 interactions by hand if you've got a particularly large unit cell file.
Okay, so there are a couple of questions. The first one, can you explain a bit how the DMI goes into the exchange tensor? So the DMI calculations are based on the relative positions, and this gives you the direction of the DMI vector, and then you have the strength of the interaction, which will be multiplied to this, and it will go into the antisymmetric part of the exchange tensor. If you have ab initio parameters, then in principle, you should have already the full exchange tensor. So you can plug that in directly into your atomistic spin dynamics simulation. So that's good for, usually for in this kind of case, you have long range interactions. But even if you want to do with the kind of constant strength of DMI or something like that, you can always calculate the neighbor list. And then another question is how to incorporate the DMI value, which changes layer by layer exponentially. So via the unit cell file, you can, so if you want to do this via the unit cell file, you need actually to calculate, I think, the full stack of the material. So if you have, for example, 3 layers, you can calculate the unit cell file for those 3 layers, and the DMI strength you put in those 3 layers should depend on the exponential one. If you want to use the in-bid method, then you can do that by adding in your material file different DMI strengths. So in the material file, you have something like material 1 interacts, the DMI exchange in material 1 is mediated by some heavy metal, for example, and have this strength. So then you can construct another material on top in which you can change the strength of that and so on. So you cannot do it directly in the code, but you can do this by modifying either your material file or try to construct a UCF file that kind of has that properties. And another question, if we have tried to include dipolar interactions in system with DMI, if this is so, how do they influence the Skyrmion formation? So I've actually tried this for a system, and well, the dipolar interaction should, in principle, stabilize the Skyrmions, and I've actually managed to see that in some particular systems. So even if you have DMI, the DMI was quite small in that particular system, but then if you add the dipolar interaction, they start to be more stable. So in principle, dipolar interaction, the strength of the DMI, or even kind of longer, higher order exchanges can stabilize this structure. So in principle, if your system is large enough in order to include dipolar interactions, then this will definitely stabilize your Skyrmions, so will be helpful. But as well, this depends on the size of your Skyrmion. So if you talk about Skyrmions with very small sizes, then the contribution from dipolar interaction is quite small, so it doesn't really make sense to include. But then if you go towards larger system size, then it's important to include them. Do they change the Skyrmion size? I haven't looked, but in principle, I think it should be an effect. So I haven't looked. I don't know. So
Can I ask a question?
Go ahead.
So jumping back just to the exponential layer by layer one, Skyrmions, they're generally only a very few number of layers. Is that correct? They're sort of a thin film effect. You don't get them in a bulk.
You could.
You can.
Depends which type also of you might. So the one we are looking at usually, yes, are just in thin films, or you can have them in repetitions of like cobalt platinum.
Just would be curious to know, because there's sort of various system building things that we want to do at some point, like changing concentrations in a gradient of a particular alloy, something like that. So you have at the bottom a lot of something, at the top not a lot. So just curious to see if this sort of exponential repeating something like that is something that would be coming up a lot. Because it's fine to do for 4 layers or even 10 layers or something, but if you've got 1,000 layers, it becomes a pain to do manually. If you could have it repeat intelligently, that would be easier. So just curious if it's going to come up a lot.
I mean, it does anyway make sense that the DMI, if you generated the interface, will decrease. I mean, it might decrease exponentially, or it could be a way to approximate the way it decays. So ideally, maybe a good thing we could implement is to, again, give this kind of trend for interactions, so that when you just ask, for example, I don't know, an exponential or a polynomial or a linear one, and you just get them.
Yeah, I mean, in principle, even if it shouldn't be hard to implement something like that, because it's all pre-processing. Vampire doesn't have to calculate that on the fly, because you could just generate an input file sensibly with that sort of information. It's just whether or not the input file, whether or not we can make it faster to have Vampire generate it than to generate it sort of manually. Because once you generate it manually, you're limiting, you're always going to have these columns as your unit cell, and that could be slower if your columns are very big. So you could be putting a lot of atoms onto each core, for example, something like that. So it's just something that we might have a look at, if it is something that people are possibly going to use. I've only ever really seen Skyrmions as thin film things, but if they appear in other places, then yeah, it's certainly an interesting idea. I don't know if anyone's got any questions that are related to anything else, or anything else in the unit cell files, things like that. If people are kind of running out of Skyrmion questions, or if people have more Skyrmion questions. But yeah, if you want to ask anything else about unit cell generation or things like that, if you don't think of anything now, later on today there is the complex crystal structures Q&A, which will be a lot of information about unit cell files, obviously. I think in principle, can't they, at really low temperatures?
Without field.
there is a paper by they do with the laser pulse.
Sorry, we should read the question out. I don't know if the chat gets recorded.
Ferrite magnet skyrmions be formed without external field. I remember about the publication trying to generate that with the ultra-fast laser pulse. So in principle,
yeah, I think they're very unstable, though, aren't they, without the field?
No. So those were really big
Oh, okay.
magnets. So I think what they observed, they were quite stable, and there was also a dependence of their size upon the laser pulse fluence. So in principle, I think you can without a field, but you need some sort of excitation, like an ultra fast excitation to do that.
Is there when do they stop being skyrmions and start being domain walls? How big do they have to be before they're just, you know?
It's more the way there are properties like the charge, topological charge, and the properties that you kind of use to define skyrmions. I mean, they can behave.
So if you have if you make a skyrmion big enough, though, you've got a section of upspin and then a sort of wall around it and a section of downspin. You know, that's, you know.
Because they will vary. So the point is the way they vary. There are now all these different definitions. So it really is not decisive. The only issue might be if you go on a 3-spin, you know, if your skyrmion is on 4 spins, so you have a 10 or what's that, 4 or 5, the minimum amount of spins you can have to get in a line, then it can be hard to define it. But as you go actually bigger, you really don't have that problem.
So as you're going along and your spin sort of they change direction, is that do they rotate more rapidly in space, not in time? Do they rotate more rapidly in space than a domain wall, or less rapidly?
It's not. I mean, that will depend on the size, really. Because if you shrink it, you will have very sharp angle changes. But if you go, you know, on a micrometer scale, then you will have very smooth variation. But that will not be a different. I mean, you want it's not the size that makes it. Usually, experimentally, they tend to get very big one.
Yeah. I like I say, not a skyrmion person.
Yeah, that's fine.
Basically just going off of Mara's presentations every now and then that tend to be of a particular size. So it's not something, because obviously sort of in very pure theory, the idea of a topological charge is a bit, there are things that you can make a topological charge theoretically that doesn't make any sense in a spin system. You know, you can have them be all sorts of weird shapes that would collapse in the real world and things. So it's just curiosity on my part. Richard wanted to know what the difference between well, I assume Richard wanted everyone else to know what the difference between normalized and non-normalized exchange interactions are. So non-normalized exchange interactions, the value at the end of your interaction line is just the strength of the interaction. So it would be something like, you know, 1e to the minus 21 joules per link, something like that. If you use the normalized keyword in your unit cell file, then the interaction value in the interaction list is multiplied by the exchange matrix value in the material file, which allows you to normalize your whole interaction list based on their distance from each other, and then multiply by an exchange later on, so you can scale the exchange of all of the exchanges with one number in the material file rather than scaling them individually. So you obviously want to use this more once you've worked out the sort of what you think the functional form of your exchange is, or at least roughly. The functional form doesn't, it's less important than you would think a lot of the time for a lot of the macroscopic effects. Beyond that, it sort of decays quite a lot. The distances for a lot of these aren't generally large enough that it's a huge effect if you change it slightly. Yeah, so you can just use the one parameter in the material file, and then that allows you to scale all of your exchanges by thing, you know, so that they can match up with things like your Curie temperature or your or any phase transitions you have in the macroscopic scale. We've got a question about checkpoints. with regards to what information is carried over to the subsequent calculations. The positions and the orientations of spins are both carried over. Statistics aren't, because you only ever output a checkpoint at the end of a statistics step. So you calculate your you have equilibration steps, and then you have sort of statistic steps where statistics are calculated over things like your magnetization things. Those, you'll never have half of those statistics be calculated before and after a checkpoint. They're always finished before a checkpoint is put out, so they won't be carried over.
You do, though, carry over the seed of your simulation. This is also what allows you to other continue restarts. So if you continue, despite whatever you put in as a seed in your input file, if you say continue, you will use the same. Whereas if you actually do restart, it will throw it away and use a new one.
Which is important, obviously, for reproducibility. If you use the same seed, you will get the same numbers in Vampire. So, there's two seeds in Vampire. There's the seed for creating materials. So if you've got like a random alloy, there's that seed. There's also the integrator seed. But if you use those both the same, you will get the same system evolving in the same way every time. In theory, at least that is the random element has been nailed down.
Then other information you carry over are, for example, temperature. So say you're calculating your M versus T, you're gonna get your temperature. Then you also, if you say, for example, you're running an hysteresis loop simulation, then you will have also the field values. And then, as Richard is writing, there's also dilution and roughness, mainly the properties that you need to keep running. What is not carried over, as Andrew just said, is the statistics mainly. That's not.
So Richard's saying there's more creation seeds than that for things like dilution and roughness, which I've honestly never looked at.
Yeah, right. Dilution and never used the roughness, yes. But it's similar to the...
Yeah. Are there you did a lot of Voronoi film work. Is there a random component to that, Andrea?
Yeah, because you can, well, the structure is kind of random. So you do your hexagonal shape usually, and then you randomly can remove atoms out of it. So again, it's very similar. So the random seed for that, but you can carry them.
Yeah, so there are these creation seeds that are all used. They're essentially, used once to generate whatever you're generating. The creation ones, because they're then inherent to the atomic positions at the end. We don't move things around in the middle of a simulation. That would very quickly break things. It's not a molecular dynamics package.
And of course, the time of your simulation, if you do some dynamics, you will know which time step you stopped.
Oh, yeah, because
otherwise that would be of a problem. Yeah.
And that is true for both Monte Carlo time steps and sort of true time steps. They both get carried over. They both, whichever one you're using would be carried over.
Well,
just one question. Can the topological charge be obtained directly? At the moment, it's not implemented in the code. However, we have a version in which we calculate the topological charge of the structures we obtain. If you think that will be a useful feature for your simulation, then just let us know. So in principle, can be added into the calculations to get it directly.
Is it post-processing?
Yeah.
Yeah. So it either could be put in as a like VDC as a post-processing step, or as a separate utility. Martin asked if the Gilbert damping constant, for example, could be changed between checkpoints, and yes, that could be changed completely. Nearly all of the material parameters could be changed, just not positions. And I think interactions even can be changed completely between, you could go to suddenly having a non-interacting material, for example, but atomic positions can't change. Although I'd have to double check if you're allowed to change positions. I'm pretty sure you can because they get read in after the checkpoint.
That's one of the main properties.
Yeah, exactly. So. I think in principle, I believe you can even change the type of integrator you're using. I'm kind of asking Richard here to see if he, yes, Richard says. So you could simulate something like getting down to equilibrium, like if you're doing a field call or something with Monte Carlo, which is generally better for things like that. And then you could look at dynamics in the second stage using the LLG Hoyan integrator. To save yourself some CPU time. The LLG integrator and the Monte Carlo are not that different in speed generally. So unless you've got a really, the Monte Carlo is only really much worth using if you're very concerned about something like the size of your system or how long it's going to run. And obviously only gives you equilibrium macroscopic properties. It doesn't evolve in true time. It involves in Monte Carlo time, which isn't quite the same. With regards to the other integrators that you could switch to, there's a midpoint LLG method, which I don't think is generally used a great deal. And then obviously there's the constrained Monte Carlo integrators that I think Andrea will talk about later today, or is it tomorrow?
Tomorrow.
There's the general constrained Monte Carlo and then the hybridized constrained Monte Carlo. That Andrea will go through tomorrow, and the YouTube video for that's already up, isn't it?
Yeah, all the tutorials are there. If people have some question already about it or they want to know something more, I can try to do some more tutorials or add some very few things.
Yeah, I mean, if we get to the end of the week and people have particularly repeating burning questions, then we'll work out a way of making sure those are answered. Whether it be more videos or extra manual entries or something.
Any other questions, comments?
So officially, that's 11 o'clock. If there aren't any more questions,
Very sharp.
I was going to say, if there aren't any more questions appearing in the next 2 minutes or so, we'll break off. And I believe the next one starts at 2 GMT. No,
I think
not
it's
in GMT.
1.
1, so it's 2 for me.
Will be
1 for you guys.
Andrea here and Sarah about the fields, and then there will be another session at 4 with Daniel and me about complex crystal structures.
And that is at BST, British Summer Time, not GMT. we had the clocks move a couple of weeks ago, just so people's time zone differences aren't muddled with. Yeah, I'm not seeing any questions popping up, so I think we'll call it there.
Okay.
Right then. Well, thank you for coming along, guys. and thanks for asking questions and being engaged. And we'll see you all shortly.
Oh. Oh. Okay.
You just saying thank you. That's all right. We can deal with thank you.
Yeah, we can do that.
Bye.
All right. Bye bye.
Yeah.